Hello everyone, welcome to this new session on electromagnetic fields and transmission lines. Myself Dr. Sohail Rana, and today we will discuss about the capacitors. So capacitors are the devices who have two parallel plates separated by some dielectric. Now if we consider this diagram in 3D, it will help us understand the basic structure of capacitor. Here we can see there are two plates. There is one metallic plate M1 and there is another metallic plate M2. So on this plate you can see charges are distributed. So here the top plate if you observe, there are positive charges. We have all positive charges distributed on the surface of this metal 1 plate. Now here we consider the equal charge distribution. That means everywhere the charge density is same. So here we have a positive plate with all the positive charges. There is a bottom plate where we have all the negative charges on this plate. These are also equally distributed charges on the bottom plate. Now as this is a surface charge, we have to relate it with the surface charge density. Now if we relate it with surface charge density, we have rho s. What is rho s? Surface charge density is given by the creator of surface charge density, that is nothing but dq by the differential surface. If we take out a sample differential surface, we can find out the rho s for this particular differential surface. Similarly, bottom plate have surface charge density, but their charges are negative. Now this plate is connected with a battery source. We can see this is positive, negative connected to both the plates. Now this is the assembly. As soon as we apply the voltage, there will be production of electric field lines. And always the direction of electric field lines is from positive to negative. So we can say these are D is equal to epsilon E lines. So we are considering them on a 3D setup where this line is referring to Z axis and this line is referring to say x axis. So bottom plate we are considering on the floor, that is z equal to 0 position, and the top plate we are considering at z equal to d place. So we have bottom plate at z equal to 0 and top plate at z equal to d. Now let us move ahead. Now here we will see the basic relation between the charge density and surface charge density. As we have seen, surface charge density is say rho s, say rho s is nothing but dq by ds. Similarly, we have another charge density, that is electric flux density, where Gauss law states that the number of charges are equal to number of flux lines. When we are talking about a capacitor, there is a very interesting relation that there will be transfer of charges in the form of flux line. Now if we take some example of a closed circuit, suppose we have one R and we have one L, R, C and say L connected to a battery source. It is a closed path. We have R, we have C, and we have L. This is the voltage. Now, as per the definition of circuit, what is the definition of circuit? We must have, first condition is to have closed path. Now, these conductors and all, we have maintained the closed path. But what about the capacitor? Capacitor doesn't have closed path. What is there in between capacitor? Two plates. There is dielectric. That means someone can say this is open here. Then how can we call it a circuit which is closed? There may be a question. So what happens in this case? In this case, say one plate becomes positive, for example, then inside dielectric we cannot have the movement of charges. There will be movement of electrons, say they will start from negative terminal and they will go up to this plate, but they cannot jump inside dielectric and fly. But what Faraday observed, that whenever one plate is having some charge, after that if we connect another plate, there will be equal and opposite charge produced on that plate. But this transformation is not in the form of charges, it is in the form of flux, right? So this flux by Gauss law is nothing but same charge. How much flux will pass, how much charge is present, that much only it will cross. So D is nothing but, the creator of D is also charge in one sense. Say we can say D is equal to S or surface area. Now if we consider the direction of our plates are present on Z axis. So these lines, direction lines, are towards minus Z axis. So we can say the direction of these field lines is minus AZ cap, right? And what we have relation between D and E, we have D is equal to epsilon E, where D and E, both of them are vectors. So this is our theory for this circuit. Now let us evaluate more relations for this capacitor. Now what is this flux? It can be defined as something which has crossed from one plate to another plate. I will draw our circuit here. So this is the circuit in 2 dimensions now. The earlier diagram we have seen in 3D. So say we have a voltage source, positive, negative. This is our capacitor C. So what we have seen, that the relation between D and E is given by D is equal to epsilon E. So from here what we can say, E is nothing but D by epsilon. Now if we consider vector and direction, then what is the direction? Say this is going down towards minus Z direction. So direction will be minus AZ cap. So this is the direction component. Now if we put it in D is equal to Q by, what is D is equal to? D is nothing but, we have just now derived, D is equal to Q by A. So if we keep this Q by A here, what we will get in this equation? We will keep this value. So we will get E bar is equal to Q by epsilon A minus AZ cap. Here also we will get minus. So this is, say, electric field intensity. But we have also derived voltage. What is the expression for voltage? The relation between voltage and electric field intensity. Say voltage for a line charge is given by say the limit from some A to B. But in this case, if we consider the plate is from 0 to D, then what we have to consider? We have to consider limits as 0 to D. That is the difference between plate. Bottom plate it has 0, top plate is at D. So what we can say, V is equal to integral starting from 0 going to D E bar dot dl bar. So this is voltage. Now here, if we keep the value of charge at the place of E bar, so what we will get? We will get V is equal to integral the limits from 0 to D. E is nothing but Q by epsilon A minus AZ cap into dl. Now what may be this dl? Now this is also vector. It may have three directional component. Whoever is a vector will have direction as well as magnitude. So what may be the three possible axes for dl? Dl may be equal to dx ax cap plus dy ay cap plus dz az cap, right? So now we can put it in our expression. So what we will get? We will write the expression. So say so V will be equal to, new expression for V we will write down. So V is equal to line integral from 0 to D. E is Q by epsilon A. So if we consider the direction, what is direction? We have direction of AZ. Then if we put all of them, say dx ax cap plus dy ay cap plus dz az cap. Now if we take multiply this direction with all of them one by one. So if we take the multiplication of az into ax, what is the rule? If any dissimilar directions are taken dot product, the answer will be 0. So az cap ax cap will be 0. Similarly az cap into ay cap will be equal to 0. But if we have similar direction, unit direction product, then it will be equal to 1. So by keeping this, our equation will reduce. For voltage, say voltage will become 0 to D, then we have Q by epsilon A, and what will be the remaining term? dz. Az dot az will become 1. So it will be, say, dz, because we are moving in z direction. We will take out the constants. So what we will get? V is equal to Q by epsilon A integral of dz. If we integrate dz, we will get z, and we will put the limits. So what we will get? We will get V is equal to Q by epsilon A z from 0 to D. So what we will get? The final answer, we will get Qd by epsilon A. Why we are calculating voltage? I will tell you. So V will be equal to Q D by epsilon A. Now this is the voltage. Now what we are using this voltage as? This voltage is involved in the definition of capacitor. If we observe the diagram of capacitor, we have one positive plate, one negative plate. Then capacitance, in this capacitor is defined as the charge per voltage, how much charge is being stored for the given voltage. That is nothing but capacitor. What is function of capacitor? To charge. It will have charge. So this charge, how much charge is acquiring for given voltage, that is nothing but C. So from here we can find out C. So what we will do, we will write down expression for C here. So as per definition, C is equal to charge per voltage. Already we have calculated this voltage. So what we can say, Q divided by QD by epsilon A. So this Q will get cancelled. So if we replace the term, what we will get? C will be equal to epsilon A by D. This will be the formula for capacitance. So this is capacitance for parallel plate. What is this? This capacitance formula for parallel plate. Now we have to conclude few points here. Then we will see the spherical capacitor. So say what points we have to remember out of this. First one we have to remember is that permittivity of dielectric material is very important in the expression of capacitor. So permittivity, what is C formula? C formula is equal to epsilon A by D. This epsilon can have value of epsilon naught, epsilon R. That is the permittivity of medium. It is directly related with the permittivity. So permittivity of dielectric material is very important. How much he is allowing the flow, how easily he is allowing the flow is of course very important. Then capacitance depends on the cross sectional area of the plate. How wide these plates are there, that is also important, directly proportional to the area. Then capacitance also depend on the distance between two plates. What is D? If distance is decreased, capacitance increases because it takes less time to handle the movement of flux across these two plates. It is not dependent on the voltage, charge or electric field intensity directly. So this expression directly does not depend upon any of the charge, voltage or electric field intensity. So that's very important point to remember. Now let us see spherical capacitor. So what is our topic now? Our topic is to discuss spherical capacitor. Now for that we will imagine this diagram where we can see what is meaning of spherical capacitor. We will imagine a sphere that is nothing but like a dot. So there is a inner sphere of some radius A and there is some outer sphere with radius B. So there are two spheres, right, and they are separated by some dielectric medium between them. In 3D we can easily see that. So inner one is connected with positive, so outer one will be grounded. Two spheres separated by dielectric. So this is also called as the Gaussian surface. What we can call it as? We can call it as Gaussian surface. So this is our setup. Now in this case we have to consider the spherical system, so our equation will be slightly changed. So let us see how our setup changes with this. Now spherical coordinate system. A sphere is directly related with some kind of charge. If we zoom the charge, if we consider a charge, say this is the charge, a single point present, a simple charge q. Now if we zoom it, what we will get? We will get a shape of a sphere. That's what we imagine. So we consider spherical coordinate system. So for this charge, again we will start with the basic relation of electric field intensity. What is electric field intensity? For a given charge, it is given by q by 4 pi epsilon naught r square. If we consider vector, we have to consider the direction ar cap. Now when we deal with a dielectric, then we can use the relation of Gauss law, that is nothing but psi is equal to q. Now we have also derived the relation of voltage. We have fixed steps. We have electric field intensity, we derive voltage. When we derive voltage, we derive capacitance by using the formula, that is charge per voltage. So we will be equal to, we have integral of E bar dot dl bar. Now here we can keep the value of this q. So what we can write? We can write V is equal to minus of q by 4 pi epsilon naught r square into ar cap. Now we have to consider the limits. We have two spheres. We are saying two spheres. One is inner sphere, one is outer sphere. Inner sphere have, say, radius. One is having radius a, another is having radius b. So if we consider the final two initial limits, so we have to put, say, b to 1. So this is about the limit. Now what is the differential length? Differential length here is directly related with the radius of the sphere. So what we can say? We can say here q. What we can write? Q, along with q we have this differential length dl. This dl is nothing but dr ar cap. So let us further keep these values. So once we keep the values, we will get V is equal to we will get V is equal to B to A q by 4 pi epsilon naught r square ar cap into dr into ar cap. This ar cap dot product will become 1. So what will be the reduced expression here? V will be equal to B to A q by 4 pi epsilon naught r square into d r. So further we will expand this. Now here we can see So here we have V is equal to limit from minus B to A Q by 4 pi epsilon naught R square dr. Now all others are constant, we have to just integrate dr. So for dr we will get 1 upon R square. So if we take integration of 1 upon R square, so we will simplify it, we will get minus 1 upon R. The limits will be for R equal to A to R equal to B. So those limits we can put here. So after keeping the limits, so we will get V is equal to Q by 4 pi epsilon naught R Q by 4 pi epsilon 1 by A minus 1 by B. Now what is our remaining work? Our remaining work is to just keep it in formula C is equal to Q by V. So here we can keep C is equal to Q upon, we will keep the value of V as Q upon 4 pi epsilon 1 by A upon 1 by B. So once simplify, we will get C is equal to 4 pi epsilon divided by 1 upon A minus 1 upon B. This is the formula for capacitance. So with this we will stop this session. Next session we will see the next topic related to electromagnetic fields and transmission line. Till then, have a good day. Thank you.